Behind every flawless component lies a battle against heat, vibration, and tolerance drift. High-speed machining pushes materials to their limits. The real question: how close to perfection can steel be shaped? From the controlled heat of massive furnaces to the precision of advanced inspection systems, Francini Acciai represents a benchmark in large-scale steel forging across Europe. Production begins with high-quality ingots sourced from leading European steelworks. Careful raw material selection forms the foundation for reliable forged components. Ingots are cut to optimize dimensions using an advanced cutting department equipped with more than 20 saws and an oxy-fuel cutting system, ensuring efficiency and material yield. Forging stands at the core of operations. A fleet of 10 furnaces, with volumes reaching up to 450 cubic meters, heats ingots to precise temperatures, including hot charged material delivered directly from steelworks. Heated ingots are processed on open die presses rated at 2, 500, 3, 500, and 8,000 tons, supported by automated manipulators capable of handling components weighing up to 100 tons. Operations include upsetting, drawing, mandrel forging, and specialized deformation processes. Heat treatment follows in a dedicated department where rail-mounted furnaces reach temperatures up to 150 degrees Celsius. Controlled quenching in water or polymer tanks, assisted by adjustable propellers, ensures uniform metallurgical properties for components up to 24 meters long. CNC machining centers perform rough and finish machining, while comprehensive quality control governs every stage. Non-destructive testing includes ultrasonic inspection, magnetic particle and die penetrant testing, dimensional checks, hardness testing, and heat stability verification. Destructive testing and chemical analysis are conducted in an in-house laboratory. Finished forgings are shipped worldwide by road, sea, or air. Certified quality systems, international approvals, and a strong focus on innovation ensure Francini Acciai products meet the strict technical requirements of energy, oil and gas, marine, nuclear, and heavy engineering industries. Before becoming a precision-engineered industrial component, each massive forging at Bruck GmbH begins as raw metal shaped by heat, force, and exact control, where every movement transforms weight and power into engineered reliability. The process begins with the transport of massive, solid metal blocks to the production facility. These raw forgings are first trimmed, with excess material removed from the ends to achieve the required length and prepare the workpiece for further processing. The prepared block is then transferred into the hot forging line, where it is heated to carefully control temperatures. At this stage, the material becomes formable without compromising its internal structure. Through a seamless hot rolling process, the heated metal is shaped into a continuous circular form, creating a large, seamless ring with uniform grain flow. This step is critical, as it ensures high structural integrity and mechanical strength throughout the entire component. Once the basic geometry is achieved, the ring is moved to advanced CNC machining centers. Here, high-precision machining operations define the final dimensions, profiles, and functional surfaces. Complex contours and tight tolerances are achieved through multi-axis CNC systems, ensuring the component meets exact design specifications. Dimensional accuracy is then verified using a coordinate measuring machine. The CMM inspects the large, seamless ring or bearing component in 3 dimensions, comparing measured data directly with digital models to confirm geometric precision. Following this, selected areas undergo weld overlay processes, where additional material is deposited to enhance wear resistance or restore functional surfaces subject to high loads. Quality control is conducted at multiple levels. Digital inspection systems and calibrated measuring devices verify dimensions, while ultrasonic non-destructive testing is applied to detect internal flaws without damaging the component. Specialized lighting systems support visual inspections, revealing surface imperfections that may not be visible under normal conditions. After passing all inspections, the component enters the finishing phase. Protective coatings are applied through controlled painting processes, ensuring corrosion resistance and long-term durability. The Bruck GmbH logo and identification markings are then engraved, providing full traceability and product authentication. With all processes completed, the forged component is fully finished and ready for integration into larger assemblies, delivering reliability, strength, and precision for demanding industrial applications. The construction of the reactor vessel at Atom Mash represents one of the most demanding achievements in heavy nuclear manufacturing. The process begins with large-scale smelting and forging, using ingots weighing up to 360 tons and hydraulic presses delivering forces of up to 15,000 tons to form ultra-thick reactor-grade steel components. The vessel flange is machined with 54 threaded stud holes and precision wedge-shaped grooves, designed to house rod-type gasket rings, ensuring a reliable and tight main reactor joint. Nozzle shell rings follow, among the most complex elements of the reactor vessel. Each ring integrates inlet and outlet nozzles, 5 emergency core cooling system nozzles with 300 mm diameter, and 1 large 850 mm nominal diameter nozzle, all requiring extreme dimensional accuracy. The support shell ring incorporates a reinforced rim that carries the entire reactor structure. Above it, the central shell ring operates under intense neutron irradiation, making its metallurgical integrity critical to reactor lifetime. The lower shell ring and elliptical bottom head complete the pressure boundary, supporting internal structures and maintaining precise spacing of fuel assemblies. After forming, components undergo extensive mechanical treatment, plating, assembly, and multi-pass welding. Heat treatment relieves residual stresses, followed by X-ray inspection and hydraulic pressure testing. Only after full verification is the reactor vessel approved for delivery. At Holroyd, screw and rotor manufacturing is a highly controlled precision process where geometry, surface quality, and micron-level accuracy define final performance. Production begins with carefully selected steel billets, which are pre-machined to establish reference diameters and centers before entering the rotor manufacturing line. The core of the process takes place on advanced CNC rotor milling and grinding machines, purpose-built to generate complex helical profiles. Using synchronized multi-axis control, each screw or rotor is cut with exact lead, pitch, and flank geometry, ensuring perfect meshing in twin-screw compressors, pumps, and vacuum systems. Temperature control and vibration damping are critical at this stage to maintain dimensional stability throughout long machining cycles. After rough machining, precision grinding refines the profile to final tolerance. Holroyd's proprietary grinding technology delivers exceptional surface finishes, reducing friction, leakage, and wear during operation. In-process measurement systems continuously monitor profile accuracy, allowing real-time corrections and repeatable quality across production batches. Once machining is complete, components undergo comprehensive inspection. Coordinate measuring machines, profile scanners, and surface roughness analysis verify geometry down to microns. Where required, rotors receive surface treatments or coatings to improve corrosion resistance and service life. The final stage focuses on balance and functional integrity. Dynamic balancing ensures smooth, high-speed operation, while traceability records document every machining and inspection step. Through this tightly integrated process, PTG Holroyd delivers screw and rotor components engineered for efficiency, durability, and long-term reliability in demanding industrial applications. The assembly of one of the largest screw compressors ever built by Howden showcases heavy engineering at its highest level. Massive rotors, precision machined to micron tolerances, are carefully aligned within a robust cast housing. Each assembly stage focuses on exact clearances, bearing preload, and sealing integrity. Integrated drive systems, oil injection components, and control modules are installed methodically before final testing. The result is a high-capacity compressor designed to deliver stable performance, exceptional efficiency, and long-term reliability in extreme industrial environments. Inside Horsburgh and Scott's manufacturing floor, large industrial gears are shaped on heavy-duty boring mills and vertical turning machines built for extreme precision. An open-side ferrule boring mill handles components up to 20 feet in diameter on a 20-ton table, with an extended column allowing workpieces as large as 50 feet. Over decades, gears exceeding 40 feet have been machined in a single setup. A live spindle allows drilling and tapping of bolt circles without repositioning. Alongside it, A Giddings and Lewis vertical turning center machines parts up to 94 inches in diameter. Dual live spindles support turning, milling, drilling, and tapping in one operation, while a pallet changer enables parallel setup and cutting, keeping the process continuous, efficient, and highly accurate. Productivity drops the moment a machine comes to a halt, and at the center of that risk lies the spindle, the most critical yet unseen component. At DN Solutions, spindle rebuilding follows a tightly controlled manufacturing-grade process. Damaged spindles are machined to micron-level accuracy using certified original parts only. Each component is verified with 3D coordinate measurement, ultrasonically cleaned, and thermally stabilized in a climate-controlled clean room. Assembly is performed by experienced engineers using proprietary procedures developed over decades. Bearings are preheated, dimensions are logged, and run-out, vibration, noise, and thermal tests are conducted across the full RPM range. Only spindles that meet strict performance criteria are approved, protected, documented, and delivered worldwide, ensuring long-term precision and reliability. Inside a modern machining cell, the CNC mill turn center demonstrates how complex shaft components are produced in a single, tightly controlled workflow. Raw shafts are loaded and precisely clamped to ensure perfect concentricity before machining begins. The mill turn concept combines high-performance turning with full 5-axis milling, allowing multiple operations to be completed without repositioning the workpiece. Rough turning is carried out first, removing excess material and establishing the primary shaft geometry. Once the basic form is defined, milling units engage to machine keyways, splines, grooves, and complex contours directly on the rotating shaft. Driven tools and synchronized axes enable drilling, tapping, and cross-machining with micron-level accuracy. Throughout the process, continuous tool measurement and in-process probing maintain dimensional stability, even on long or heavy shafts. Internal coolant delivery and optimized chip evacuation protect surface quality and extend tool life during high-load cutting. The rigid machine bed and advanced spindle design minimize vibration, ensuring consistent results along the entire shaft length. By integrating multiple machining steps into one setup, the WFL mill turn process significantly reduces handling time, alignment errors, and production cycles. The result is a fully machined shaft that meets strict tolerances for use in power generation, marine propulsion, heavy industry, and advanced mechanical systems, delivered with efficiency, repeatability, and uncompromising precision. Continuously transposed conductors, are high-efficiency conductors used in power transformers. Multiple insulated rectangular copper or aluminum wires are continuously transposed along the length, minimizing eddy current losses, balancing current distribution, reducing hot spots, and improving overall electrical and thermal performance. Maintenance partners completed the rewinding and high-speed balancing of a 15 MVA generator rotor within 8 weeks. The overhaul included dry ice cleaning, epoxy support renewal, precise rotor rewinding, RSO testing, and dynamic balancing up to 3,600 revolutions per minute, ensuring electrical integrity and operational stability. At Brush Electrical, a full Stator rewind and core rebuild for EDF Energy is executed as a comprehensive, end-to-end engineering operation. Coil manufacturing is carried out in-house, allowing full control over conductor selection, insulation systems, and dimensional tolerances. Once completed, coils are installed through a controlled winding process designed to ensure uniform mechanical restraint and optimal electrical clearances. Extensive testing is performed throughout the rebuild, including insulation resistance, surge, and high voltage tests, verifying compliance with operational and safety standards. Heavy lifting operations are supported by craneage rated up to 40 tons, enabling safe handling of large stator cores and winding assemblies. Dynamic load testing capabilities allow the stator to be evaluated under simulated operating stresses, ensuring long-term reliability. The result is a rebuilt stator core and winding system restored to reliable long-term operational performance. Golin S/A operates a comprehensive industrial manufacturing system focused on the production of welded carbon steel tubes, engineered components, and specialized industrial services. At the São de Boa Vista plant, the production process is dedicated to industrial carbon steel tubes in square, rectangular, and circular profiles, designed to meet strict structural and dimensional requirements. The process begins with high-quality carbon steel coils, which are carefully inspected and prepared before entering the forming lines. The steel strip is progressively shaped through a series of roll-forming stands until the desired cross-section is achieved. High-frequency welding is then applied to close the profile, creating a continuous and uniform seam with excellent mechanical strength. The weld bead is precisely trimmed, and the tube passes through calibration and sizing stations to ensure accurate dimensions and straightness. Once formed, the tubes undergo cutting to specified lengths and are subjected to rigorous quality control procedures. Dimensional inspections, surface checks, and non-destructive testing ensure compliance with industrial standards. Depending on application requirements, additional finishing processes may be applied to optimize surface condition and performance. The second part of the production flow highlights operations at Golin's Guarulhos units, where a broader range of steel products and services is carried out. These facilities focus on the manufacturing of shaped profiles, drawn products, and welded assemblies, supporting sectors such as automotive, construction, energy, and industrial equipment. Advanced CNC machining centers are used to produce precision parts through turning, milling, and drilling operations. Complex welded components are assembled using controlled welding procedures that guarantee structural integrity and repeatability. A key capability within the Guarulhos units is 3D laser cutting, which allows intricate geometries and high-precision cuts on tubes and formed components, reducing secondary machining and improving overall efficiency. Heat treatment plays a critical role in Golan's production chain. The new furnace installation enables controlled thermal processes, such as stress relief and normalization, enhancing mechanical properties and dimensional stability. Supporting these operations is an in-house laboratory equipped for metallurgical analysis, mechanical testing, and process validation, ensuring full traceability and consistent quality. By integrating tube manufacturing, component production, advanced cutting technologies, heat treatment, and laboratory testing within a single industrial ecosystem, Golan S/A delivers complete steel solutions tailored to demanding industrial applications. This combination of process control, technological investment, and technical expertise positions Golan as a reliable partner in the supply of carbon steel tubes, parts, and value-added services for both domestic and international markets. Handu Steel's cold-drawn tube production is built around a tightly controlled, end-to-end manufacturing process designed for precision, consistency, and mechanical reliability. Production begins with ERW mother tubes manufactured in-house at the Jinju Ibensong plant. Steel coils are slit to specification, formed into tubular shapes, and welded using high-frequency electric resistance welding. The tubes then pass through sizing, cutting, chamfering, and eddy current testing, ECT, to verify weld integrity and material soundness before entering the drawing line. At the Dangjin and Jinju Sabong plants, the cold drawing process starts with heat treatment in a non-oxidizing furnace at temperatures approaching 900 degrees C. This stage stabilizes the microstructure, relieves residual stress, and prepares the material for deformation. Swagging and surface coating follow, optimizing surface conditions and reducing friction during drawing. Cold drawing is performed through dies to achieve precise outer diameter, wall thickness, roundness, and straightness. Multiple drawing passes may be applied depending on dimensional requirements. Post-drawing, tubes undergo straightening to correct alignment, followed by cutting to customer-specified lengths. Quality assurance is integrated throughout the process. Dimensional checks, ECT inspection, and internal quality verification ensure compliance with strict automotive and mechanical standards. Additional secondary operations, including cutting and chamfering for component applications, are carried out on-site. This integrated, process-driven approach allows Handu Steel to consistently produce high-precision, cold-drawn tubes for automotive, mechanical, and industrial systems, combining metallurgical control with repeatable manufacturing accuracy. Industrial hose manufacturing is a precise multi-stage process designed to produce flexible components capable of withstanding extreme pressure, temperature, and mechanical stress. The process begins with raw rubber, delivered to the factory in long strips. Depending on performance requirements, manufacturers select from dozens of rubber formulations. In this case, natural rubber is used. Pigment tablets are added, and the rubber is mixed and heated in a mill until it becomes soft, uniform, and workable. The processed rubber is then fed into a calender, where it is rolled into continuous sheets with tightly controlled width and thickness. These sheets pass over cooling rollers and are wound into production rolls, separated by a polyliner film to prevent sticking during storage. Before hose building begins, attachment dimensions are carefully verified, as fittings vary by application. Hose construction takes place on a rotating mandrel, which defines the internal diameter and overall length. Layers of rubber are wrapped at a controlled overlap angle, followed by multiple layers of rubber-coated synthetic fabric to reinforce the hose wall. Additional reinforcement is added around fittings, after which high-strength nylon tape is tightly wound to eliminate trapped air and compress the structure. Carbon steel wire is then applied to prevent kinking and collapse under vacuum conditions. The assembled hose undergoes vulcanization inside an autoclave at approximately 150 degrees Celsius. Heat and pressure cure the rubber, permanently bonding all layers into a single elastic structure. After cooling, the hose is removed from the mandrel, trimmed, dimensionally inspected, and prepared for delivery. The result is a highly engineered industrial hose built to perform reliably in demanding environments. At Flowserve's Desio facility in Italy, valve production follows a tightly controlled industrial workflow that integrates engineering, manufacturing, and quality assurance. The process begins with advanced design, where CAD and simulation tools define pressure ratings, flow paths, and material behavior under extreme operating conditions. Cast components are produced to precise metallurgical specifications, ensuring structural integrity and corrosion resistance. Once cast, parts enter CNC machining lines, where critical sealing surfaces, bores, and interfaces are finished to tight tolerances. Quality is embedded throughout the process, with dimensional checks, material verification, and traceability applied at every stage. Automated and manual assembly stations then integrate bodies, trims, actuators, and sealing systems according to documented procedures. Safety is treated as a core engineering requirement, reflected in both workplace practices and product design standards. Each valve undergoes rigorous functional and pressure testing, validating performance, reliability, and compliance with international industrial specifications before delivery. Precision machining on the DMC-85 monoblock demonstrates how advanced mill-turn technology consolidates complex operations into a single, highly controlled workflow. The process begins with turning using a tilted rotary table, a turning tool, and a W-plate, allowing stable material engagement while maintaining optimal cutting angles. High-efficiency roughing follows, executed at feed rates up to 12,000 mm per minute using an E63 corner cutter head. This aggressive material removal stage rapidly establishes the basic geometry. Inner and outer contours are then roughed with a 16 mm end mill, preparing the part for precision finishing. The inner contour is refined using a E12 mm ball nose cutter, achieving smooth transitions and accurate surface definition. After the second clamping, turning operations resume with the turning tool and R-plate to rough the main turning contour. Inlets are roughed using a 40 mm corner cutter head, ensuring consistent geometry and controlled material flow. The process then transitions into advanced multi-axis machining, including 4- and 5-axis simultaneous roughing to efficiently shape complex features. A critical step involves 5-axis simultaneous roughing of internal pockets with a 12 mm end mill, followed by overhead machining that enables free chip fall. This strategy improves chip evacuation and thermal stability. Barrel milling with a 12 mm cutter further enhances surface quality while reducing cycle time. Interpolation turning with a grooving turning tool introduces precise rotational features, while 4-axis finishing with a 16 mm end mill refines critical surfaces. The inlets undergo a final finishing pass to meet tight dimensional tolerances. Advanced stages include 6-axis interpolation turning using a turning tool and V-plate, demonstrating the machine's full kinematic capability. The process concludes with 5-axis simultaneous finishing using a Liège 12 mm barrel milling cutter, delivering high surface integrity and geometric accuracy. This integrated mill turn workflow highlights the DMC 85H monoblock's ability to perform complex machining with fewer setups, higher precision, and maximum process reliability. Heavy machining with Seco tools showcases controlled, long-duration cutting on a massive rotor shaft, where stability and tool life are critical. In this operation, a 25 metric ton rotor shaft is subjected to super heavy turning with a deliberately optimized material removal rate, maintaining a smooth, uninterrupted cut over extended cycles. The process relies on a cost-effective, screw-clamped SCMT38 positive insert, selected for its reliable seating and consistent edge performance under high loads. Seco's Duratomic TPO500 coating plays a decisive role, delivering exceptional wear resistance, thermal stability, and edge toughness when machining demanding materials. This coating allows higher cutting speeds while preserving predictable wear patterns, reducing unplanned tool changes. Combined with rigid machine setup and controlled cutting parameters, the result is stable chip formation, excellent surface integrity, and efficient stock removal on large-scale components. The operation demonstrates how advanced insert geometry and coating technology enable safe, productive, heavy turning in extreme machining environments. This forming machine transforms round steel tubes into precisely shaped square tubes and specialized profiles, such as drill-pointed ends, through a controlled cold forming process. The operation begins with round tubes fed into a series of calibrated roller stations. Each set of rollers gradually reshapes the circular cross-section, applying uniform pressure to form sharp corners and flat faces without cutting or welding. Dimensional accuracy is maintained through fine adjustments in roller alignment and spacing. For drill point tube formation, the machine uses progressive shaping and pressing tools to taper and contour the tube end into a pointed geometry suitable for ground anchoring or drilling applications. Throughout the process, material flow is carefully controlled to prevent thinning, cracking, or distortion. The result is a high-strength, consistently formed tube with precise geometry, ready for structural, construction, or industrial use, achieved with high efficiency and repeatability. At BPB Argentina, the manufacturing of tapered roller bearings is driven by a high level of industrial automation designed to ensure consistency, precision, and repeatability at every stage. CNC machining centers automatically process bearing rings with micron-level accuracy, controlling geometry, surface finish, and dimensional tolerances. Automated heat treatment lines regulate temperature, time, and cooling cycles to achieve uniform hardness and optimal metallurgical structure. Robotic handling systems transfer components between machining, grinding, and assembly stations, minimizing human intervention and reducing variability. Automated grinding machines perform raceway finishing with real-time monitoring of roundness and surface roughness. During assembly, semi-automated lines control roller placement, cage alignment, and preload adjustment. Integrated inspection systems use sensors and vision technology to verify dimensions, concentricity, and rotational performance. This automation-focused production approach allows BPB to deliver reliable, tapered roller bearings that meet demanding industrial and agricultural applications while maintaining high productivity and consistent quality standards. Varex's engine valve solutions demonstrate a highly controlled, end-to-end manufacturing process designed to meet the extreme thermal and mechanical demands of modern internal combustion engines. Production begins with bar shearing, where alloy steel bars are cut to precise lengths, ensuring consistent material input for downstream operations. The valve stem and head materials are then joined using friction welding, a solid-state process that delivers high joint strength without compromising metallurgical integrity. Following welding, upset forging shapes the valve head and transitions, refining grain flow for improved fatigue resistance. The forged valves pass through a continuous furnace heat treatment, where temperature profiles are tightly regulated to achieve the required hardness, toughness, and microstructure. A seat deposit is then applied, typically using advanced alloys to enhance wear and heat resistance at the valve-to-seat interface. The process continues in the machining area, supported by auto-loading systems and bowl feeders that ensure consistent, high-throughput handling. Rough end grinding establishes initial dimensions, followed by automated transfer-to-profile turning, groove grinding, and head diameter turning and facing, where final geometry is progressively achieved. Targeted induction hardening is applied to the valve end and later to the seat area, increasing surface hardness while maintaining a tough core. Subsequent finish end grinding and seat grinding deliver the required surface finish and sealing accuracy. To enhance corrosion resistance, a chrome flash plating is applied. The manufacturing cycle concludes with automated inspection, combining dimensional checks and surface quality verification to ensure every engine valve meets Varex's strict performance and reliability standards before release. Inside a modern factory, spring coiling machines transform simple steel wire into highly precise mechanical components through a carefully synchronized process. What appears effortless is the result of exact control over force, timing, and geometry. Compression spring coilers feed hardened wire through servo-driven rollers, guiding it around a mandrel where each coil is formed with millimeter accuracy. Every rotation is calculated to achieve the required pitch, diameter, and load rating. As the process continues, torsion and extension springs are shaped using coordinated bending arms and point-forming tools. These mechanisms operate in perfect sequence, bending wire ends, forming hooks, or creating legs that will later absorb torque or store energy. Servo motors constantly adjust speed and pressure, compensating for material variations to ensure consistency from the first spring to the last. What makes these machines especially fascinating is the harmony between motion and control. Sensors monitor wire tension, feed rate, and coil geometry in real time, while CNC systems instantly correct deviations. Heat-treated steel responds predictably, allowing springs to retain their elastic properties even under repeated stress. Point-forming stations refine the spring ends, grinding or shaping them for stable seating and uniform load distribution. In high-speed lines, finished springs drop seamlessly into collection bins, each one identical in performance and dimension. There is no pause, no wasted motion, just continuous precision. These machines are not only satisfying to watch, they represent the backbone of countless industries. From automotive suspensions and industrial machinery to medical devices and consumer products, springs play a critical role. Behind every reliable spring is a coiling machine executing thousands of precise movements per minute, quietly demonstrating how modern manufacturing turns raw material into engineered perfection. A spiral duct line transforms flat steel coils into rigid, aerodynamically efficient spiral ducts through a continuous, highly controlled forming process. The operation begins with feeding a metal coil, typically galvanized steel or stainless steel, into the decoiler, where it is straightened and guided into the forming section. Precision rollers shape the strip while an integrated edge-locking system creates the characteristic spiral seam, ensuring structural strength and airtight joints without additional welding. As the strip advances, the duct diameter is continuously adjusted to meet project specifications, allowing flexible production in real time. An inline cutting unit then sections the duct to exact lengths with minimal material waste. Throughout the process, synchronized drives and servo controls maintain constant pitch, seam pressure, and dimensional accuracy. The result is a lightweight yet strong duct system, optimized for HVAC airflow efficiency, rapid installation, and consistent quality in industrial-scale production. What turns a silent steel disc into a blade capable of slicing through metal, wood, or composite materials at thousands of revolutions per minute? And why does every microscopic step along the way matter? The process starts with carefully selected raw steel, chosen for its specific alloy composition and mechanical properties. This material forms the foundation of the blade's durability, elasticity, and cutting stability. Using high-precision laser cutting systems, the basic blade geometry is cut from the steel plate. Laser cutting ensures clean edges, tight tolerances, and consistent symmetry, which are critical for high-speed rotation. Following cutting, the blade blanks undergo heat treatment. This step adjusts hardness, internal stresses, and microstructure, giving the blade its required balance between strength and flexibility. Controlled heating and cooling cycles ensure uniform properties across the entire disc. Once heat treated, milling operations refine critical areas such as slots, expansion grooves, and reference surfaces. These features help control vibration, thermal expansion, and noise during operation. After milling, the blades are lightly oiled to protect against corrosion during subsequent handling. To prevent magnetic interference during cutting, each blade is demagnetized. The bore is then inspected with precision measuring equipment to ensure perfect concentricity and fit on the arbor. Any deviation at this stage could cause imbalance at high rotational speeds. The blades are thoroughly washed to remove oils, residues, and fine particles before entering the brazing stage. During brazing, carbide teeth are precisely positioned and permanently bonded to the blade body. This operation demands exact temperature control and alignment to guarantee strong joints and consistent cutting geometry. After brazing, sandblasting cleans the surface and prepares it for further processing. The blade then undergoes tensioning, a critical step where internal stresses are intentionally adjusted. Proper tensioning ensures the blade remains flat and stable during rotation, even under thermal load. Straightening follows, correcting any residual distortions to achieve perfect flatness. Grinding is performed next, shaping the carbide teeth to their final cutting profile. This step defines cutting performance, chip flow, and tool life. Each tooth is ground with micron-level precision to ensure uniformity across the blade. Through this carefully sequenced process, Gudo transforms raw steel into a precision circular saw blade engineered for accuracy, longevity, and demanding industrial applications. A protective coating is then applied, enhancing wear resistance, reducing friction, and improving heat dissipation during cutting. Finally, the blade is marked and printed with technical information, branding, and traceability data. Inside Beatty's workshop, the saw manufacturing line runs in a steady, controlled rhythm. Steel strip coils are fed into the machine, where synchronized cutting and stamping tools shape precise saw teeth. Each movement is timed for accuracy, ensuring uniform geometry, sharp edges, and consistent spacing, ready for the next production stages. Stainless steel hollow spheres are produced through a controlled forming and finishing process. Manufacturing begins by cutting stainless steel sheets into precisely shaped blanks. These blanks are then formed into hemispheres and carefully aligned. Skilled welding joins the two halves, creating a seamless hollow sphere while maintaining structural integrity. After welding, the surface undergoes grinding to remove excess material and smooth the joint. Final polishing refines the surface finish, achieving uniform geometry and corrosion resistance. The result is a durable, lightweight stainless steel hollow sphere suitable for architectural, industrial, and decorative applications, where strength, precision, and appearance are equally critical.